Welcome to the Climate and Sustainability Coaching Session. Today we're starting with the journey through the science behind climate change. We'll examine the intricate mechanisms of global warming, understand the role of greenhouse gases, and learn from the pioneering work of climate scientists. Let's begin with the science behind the climate crisis. So, how do greenhouse gases trap heat in the atmosphere? Greenhouse gases like carbon dioxide, CO2, and methane, CH4, are fundamental to the Earth's climate system. These gases trap heat in the atmosphere through a process known as the greenhouse effect. So what? You might ask. Let's break it down. When solar radiation reaches the Earth, it passes through the atmosphere and warms the planet's surface. The Earth then emits this energy back as infrared radiation. However, greenhouse gases absorb some of this infrared radiation and re-radiate it in all directions, including back towards the Earth's surface. This process effectively traps heat in the atmosphere, leading to a warming effect. To visualize this, imagine a greenhouse used for growing plants, or glass panel windows at your house. These glass panels allow sunlight to enter and warm the interior, but they also trap heat, maintaining a warmer environment inside, even when it's cold outside. Similarly, greenhouse gases in our atmosphere let sunlight in but prevent some of the heat from escaping, thus warming the planet. French scientist Joseph Fourier first described this phenomenon in the 1820s. Fourier realized that certain atmospheric gases act like a transparent bell jar, emitting sunlight and absorbing infrared rays. He understood that the atmosphere was heated from both above by sunlight and below by infrared radiation emitted from the Earth's surface. This dual heating mechanism is crucial for maintaining Earth's climate. In the 1860s, Irish scientist John Tyndall conducted experiments to measure the amount of radiant heat that different gases could absorb. He found that water vapor and CO2 were particularly effective at absorbing infrared radiation. Tyndall's work was instrumental in identifying the key gases responsible for the greenhouse effect and laid the groundwork for modern climate science. So how does this knowledge translate to our current understanding of climate change? With the Industrial Revolution, human activities have significantly increased the concentration of greenhouse gases in the atmosphere. This heightened greenhouse effect is causing global temperatures to rise, leading to the phenomenon we know as global warming. Imagine a transparent bell jar enveloping our planet, emitting sunlight and trapping heat. This is how our atmosphere works, maintaining the Earth's moderate temperatures. But what happens when greenhouse gases like CO2 and methane concentration increase? How does this affect our climate? Why is it important to understand historical CO2 concentration levels? Understanding historical CO2 concentration levels is essential for several reasons. First, it provides context for the current levels of CO2 in the atmosphere, helping us recognize the unprecedented rate of increase. Historically, CO2 concentrations fluctuated between 175 and 300 parts per million, ppm, over the last 800,000 years. However, these levels have surged dramatically since the Industrial Revolution, reaching 412 ppm in 2019. This rapid increase correlates with human activities, particularly the burning of fossil fuels and deforestation. Scientists can track these changes and understand their impact on global temperatures by studying ice cores and other geological records. The historical data reveals that the current CO2 levels are higher than at any point in the last 800,000 years, indicating a significant human influence on the climate. The implications of these rising CO2 levels are profound. Higher concentrations of CO2 and other greenhouse gases trap more heat in the atmosphere, leading to a range of environmental impacts. These include rising global temperatures, melting polar ice caps, rising sea levels, and more frequent and severe weather events such as hurricanes, droughts, and floods. Consider the Keeling curve, a graph that has recorded a steady rise in atmospheric CO2 since the late 1950s. Named after Charles David Keeling, who began measuring CO2 at the Mauna Loa Observatory in Hawaii, the curve shows a clear upward trend in CO2 levels. This trend is not just a line on a graph. It represents a significant shift in the Earth's atmosphere and a warning sign of the changes to come. Understanding historical CO2 levels also helps us set benchmarks for climate action. By comparing current levels to historical data, we can better understand the scale of the problem and the urgency of reducing emissions. It also informs climate models and projections, helping scientists predict future climate scenarios based on different emission pathways. Picture a graph with CO2 concentrations over the last 800,000 years. For most of this time, levels fluctuated between 175 and 300 ppm, but in the 20th century, concentrations skyrocketed, reaching levels never seen before. What does this mean for our planet? Now let's discuss radiation force. What is radiation forcing, and how does it relate to global warming? Radiative forcing is a measure of the influence of factors like greenhouse gases on the energy balance of the Earth's atmosphere. It quantifies the change in energy fluxes caused by these factors. Positive radiative forcing indicates a warming effect, while negative radiative forcing suggests cooling. Radiative forcing is measured in watts per square meter. It helps scientists understand how changes in greenhouse gas concentrations affect global temperatures. For example, the increase in CO2 and other greenhouse gases since the pre-industrial era has resulted in positive radiative forcing, leading to a net warming effect on the planet. This concept is crucial for climate models and projections. By calculating radiative forcing, scientists can estimate future temperature changes and assess the potential impacts of different mitigation strategies. For instance, reducing CO2 emissions can lower radiative forcing, thereby slowing the rate of global warming. Radiative forcing is not limited to greenhouse gases. Other factors such as aerosols and land use changes also contribute to the Earth's energy balance. Aerosols, tiny particles suspended in the atmosphere, can have both cooling and warming effects. For example, volcanic eruptions release large amounts of aerosols that reflect sunlight and cool the planet. On the other hand, black carbon soot from burning fossil fuels absorbs sunlight and contributes to warming. Understanding radiative forcing helps us grasp the complexity of the Earth's climate system. It highlights the importance of addressing all contributing factors, not just CO2, to mitigate climate change effectively. Let's dig into a specific example to understand this better. The IPCC's fifth assessment report emphasized how radiative forcing influences the Earth's surface temperatures. The report introduced the concept of representative concentration pathways, RCPs, which are scenarios that include projections of greenhouse gas concentrations, air pollutant emissions, and land use changes. These RCPs help us understand potential future climate outcomes based on different levels of radiative forcing. Consider the concept of radiative forcing. It's like a heat trap that amplifies the warming effect of greenhouse gases. How can understanding this concept help us address climate change more effectively? As we conclude this coaching session, reflect on the intricate science behind climate change. Understanding these mechanisms is crucial for developing effective strategies to combat global warming. Stay tuned for our next episode, where we explore policy frameworks for climate action. Don't forget to share this knowledge with others who are passionate about sustainability or just simply curious.